Module 2, Lecture A, Autograd Mechanics. By the end of this lecture, you will be able to describe how PyTorch builds dynamic computation graphs and uses them to compute gradients. Use requires grad, backward, and grad attributes to compute and inspect gradients for simple tensor operations. And control gradient tracking with torch.nograd and detach to optimize performance and avoid unintended graph creation. Dynamic computation graphs. Dynamic versus static graphs. Dynamic computation graphs in modern deep learning frameworks are built on the fly as the program runs rather than being fixed in advance. Unlike static graphs, which are pre-designed and rigid, dynamic graphs change with each operation and follow the actual control flow and data at runtime. This makes the graph a live record of the computations during the forward pass, allowing it to adapt naturally to changes in the program's behavior. Dynamic computation graphs are created on the fly as a program runs, following the actual control flow, including loops and conditionals. This makes models flexible, allowing them to adjust their processing steps based on the input data. In contrast, static graphs require all possible paths to be defined in advance. With dynamic graphs, operations are recorded as they occur, so complex behaviors can be written directly in normal code, without separate graph construction steps. A dynamic computation graph is like a record of the forward pass that can be replayed in reverse to compute derivatives. Each node represents an intermediate tensor, and each edge is an operation that knows how to produce its gradients. After the forward pass, the framework walks backward from the output, applying the chain rule along this graph to get gradients. The graph is created fresh for each forward pass, which keeps memory use efficient and ensures gradients match the exact computations. This design allows models to handle changing real-world inputs, while the system automatically manages all gradient calculations. Python code. Dynamic versus static graphs. This material introduces a script that compares dynamic and static computation graphs in deep learning. It uses ideas from the PyTorch style of programming while working within TensorFlow. The main focus is on how control flow is handled in each type of graph and how that affects the way gradients are computed. Overall, it helps you understand the differences in behavior between dynamic and static graphs when training models. The commented line with the exclamation mark and install command is a shell instruction to install the TensorFlow library. It is usually run in a Jupyter notebook or similar environment so that TensorFlow is available to the script. Having TensorFlow installed allows the code to build and train machine learning models. Because the line is commented out, it serves as a reminder or optional step if TensorFlow is not already installed. TensorFlow is a powerful library for numerical computation and machine learning, and when we import it, it typically runs in eager execution mode. In this mode, operations are evaluated immediately as they are called in Python, rather than being deferred. This makes TensorFlow feel more like working with standard Python or NumPy, which is easier to understand and debug. Eager execution also supports more interactive and flexible experimentation, especially when building dynamic computation graphs. The script begins by printing the TensorFlow version in use, which helps you understand the exact environment where the code is running. Knowing this version is important for checking compatibility with your code and libraries. It also makes it easier to diagnose problems that may come from deprecated features or recent updates in TensorFlow. We set a global random seed to 0 using TensorFlow's random module so that all random operations in the script behave the same way every time the code is run. This means that any randomness, such as shuffling data or initializing weights, will be repeated exactly. Doing this is important for reproducibility because it allows us to reliably debug, compare results across runs, and verify that changes in output are due to code changes rather than random variation. We define a function that uses dynamic control flow and apply TensorFlow's function decorator so it is compiled into a static computation graph for more efficient execution. This compilation allows TensorFlow to optimize how the function runs. Inside the function, we perform a simple operation that multiplies the input by 2, using TensorFlow's own operations, so the computation is fully compatible with graph execution. This line uses TensorFlow control flow to perform a conditional operation. The function checks whether the input value is greater than 0. If it is, it increases another value, y, by 1. If not, it decreases y by 1. TensorFlow's conditional function handles this branching, so the computation graph can choose the appropriate path based on the input. The function produces its final result by squaring the value of y before returning it. This guarantees that the output is always non-negative and highlights the transformation applied to y. Squaring y is a standard mathematical operation, and in this context, it helps illustrate how behavior can differ between dynamic and static graph execution in TensorFlow. In this example, we define a function that runs in eager execution mode, meaning each operation is evaluated immediately. The function is used to illustrate dynamic control flow built with Python's normal language features. Inside the function, we begin by multiplying the input tensor by 2 using TensorFlow operations. This approach takes advantage of Python's natural execution flow, making it easier to write flexible and intuitive code, especially when working with conditionals and loops. This part of the code uses a basic conditional statement to change the value of a variable based on another value. When the first value is greater than 0, the second value is increased by 1. If it is not greater than 0, the second value is decreased by 1 instead. This shows a simple and clear example of using standard control flow to make decisions in a program. This function outputs the value of y multiplied by itself, which means it returns y squared. This squaring step is the final operation in both the dynamic style and static style versions of the function. In each case, all earlier calculations and conditional checks are used to determine y, and then the function returns its squared value as the final result. We create a scalar tensor in TensorFlow as a variable, initialized to the value 2. This variable is configured to track gradients, which is crucial for automatic differentiation. By defining it as a variable rather than a constant, TensorFlow can compute gradients with respect to its value. This allows us to study how changing the value of this tensor affects the output of any function that depends on it. We use TensorFlow's gradient tape to record operations, so we can later compute gradients with respect to our variables. Within this recording context, we call a dynamic style function that runs eagerly, meaning each operation is executed immediately. As this function processes the input tensor, all its computations are tracked by the gradient tape. The final output of this dynamic computation is stored in a variable for use in gradient calculations. In this example, TensorFlow's gradient tape is used to compute how the output of the dynamic style function changes with respect to the input x. Gradient tape tracks all operations applied to x inside the function, then calculates the gradient of the output with respect to x. This gradient information is essential for optimization tasks, such as training machine learning models, because it shows how adjusting the inputs can improve the model's performance. We use TensorFlow's gradient tape to record operations so we can automatically compute gradients. Within this recording context, we call a static style function that has been compiled with TensorFlow's function decorator. This compiled function processes the input tensor by applying its defined sequence of operations. The output of these operations is stored in a result called y static, which will later be used to calculate gradients. In this step, we compute the gradient of the output with respect to the input for the static style function. We use TensorFlow's gradient tape, which tracks the operations needed for automatic differentiation. After recording the computation, we call the gradient method on the tape, passing in the static style function's output and the input variable. This gives us how the output changes as the input changes, specifically within the static graph setup. The code first prints the current numeric value of the input to show what is being used in the computation. It then prints the output of a function that uses Python's normal control flow, followed by the output of an equivalent function compiled with TensorFlow's function decorator. After that, it prints the gradient of the dynamic version with respect to the input, and then the gradient of the static compiled version. Comparing these values helps illustrate how dynamic and static graph execution in TensorFlow can differ in both their outputs and their gradients. To show how dynamic style can switch between different branches, the example changes the value of a variable to -1. This new value alters the control flow inside the dynamic function. As a result, we can see how the function's behavior adjusts when the input conditions change. We now recompute the output using the dynamic style function with an updated input value. Pause. To do this, we open a new gradient tape context so that all operations are recorded for automatic differentiation. Pause. Within this context, we call the dynamic style function with the new value of the input, and it uses standard Python control flow to calculate the result. Pause. The resulting output is stored for later use when we compute gradients. We use TensorFlow's gradient tape to compute the gradient of the output with respect to the input along the dynamic path of the function. After recording the computation, we call the gradient method on the tape, passing in the function's output and the input variable. This returns how much the output changes when the input changes. In other words, it measures the sensitivity of the function's output to its input. We now use a new input value of x set to -1 to show how the dynamic function adapts to different inputs. We print this new input and then the corresponding output of the function, which changes depending on whether the input is positive or negative. Finally, we print the gradient of the output with respect to x, showing that the gradient also changes when the input changes. Together, these steps highlight the flexibility of dynamic computation in TensorFlow. This script compares dynamic and static computation graphs in TensorFlow using a simple function that doubles a scalar input, adjusts it based on its sign, then squares the result. One version uses TensorFlow's traditional static graph style, while the other relies on Python's dynamic execution. Gradients are computed for both using TensorFlow's gradient tape, and with a positive input, they produce similar outputs and gradients. When the input is changed to a negative value, the dynamic version naturally follows a different control flow and produces a different gradient, showing how dynamic graphs more easily adapt to changes in program logic than static graphs. Autograd function graph. In PyTorch, every tensor operation tracked for gradients is represented as a node in a directed graph called the Autograd function graph. As you perform operations, PyTorch records each one, including its inputs, how to compute derivatives, and its outputs. These records form a dynamic chain of function objects, where each output tensor is linked to the function that produced it, and that function knows its input tensors. This graph structure mirrors your Python computations and shows how final results depend on the original inputs. In PyTorch, you can think of the function graph as a chain of operations where inputs are transformed step by step into outputs, and each operation is represented by an autograd node. Every node knows how to perform its forward transformation and also how to reverse it for backpropagation. When you request gradients, PyTorch starts from the final output and follows these reverse instructions through the graph. This process shows how small changes in the original inputs would affect the final result, which is the essence of automatic differentiation. As your code runs, PyTorch builds the autograd graph on the fly, capturing only the operations that are actually executed. This means that any data-driven control flow, such as branching on market indicators, handling variable-length text, refining simulations, or reacting to sensor data, is faithfully recorded in the graph. Because only the taken paths become graph nodes, gradients are computed exactly along those paths. This dynamic behavior lets you freely use loops, conditionals, and other normal programming constructs while still maintaining a precise blueprint for backpropagation. Python code Autograd function graph. This script gives a beginner-friendly explanation of how PyTorch Autograd graphs work. It shows that when you perform operations, they create function nodes in the graph. The focus is on keeping the output simple and easy to understand, while still illustrating how these nodes are formed and connected during computation. The line that begins with an exclamation mark is a shell command used to install PyTorch and its related libraries, TorVision and Torch Audio. It is often run in environments such as Jupyter Notebooks to make sure these libraries are available to the code that follows. Installing them provides the tools needed to work with tensors and to perform automatic differentiation, which are essential for the rest of the script. We begin by importing the PyTorch library because it provides the core tools we need for working with tensors and automatic differentiation. This import is essential for building and manipulating computational graphs, which track how data flows through our computations. These graphs are the foundation for training neural networks and performing gradient-based optimization, so accessing PyTorch's features is a necessary first step. We begin by checking and printing the current PyTorch version. This helps confirm which release is installed and ensures that our code is compatible with it. Knowing the exact version also tells us what features and behaviors we can expect, since different versions may support different capabilities or act slightly differently. In PyTorch, we can create a tensor, which is a multidimensional array, and initialize it with values such as 2.0 and 3.0. By setting the option to require gradients to true, we tell PyTorch to track all operations involving this tensor. This tracking is handled by the automatic differentiation system called Autograd. As a result, we can later compute gradients with respect to this tensor, which is essential for optimization and backpropagation in neural networks. We first check that the tensor has exactly 2 elements. This verification is important because the following operations are designed for that specific size. By confirming the shape in advance, we reduce the risk of errors later in the computation and ensure the code behaves as intended. We build a simple mathematical expression using a tensor called x. We square the first element of x, multiply the second element by 3, and then add these 2 results to get a new value y. This example shows how elements of a tensor can be reused in different ways within a single computation. It also illustrates how such tensor operations in PyTorch form the basis for automatic differentiation. In this step, we need to make sure that the output variable y is a scalar, meaning it has 0 dimensions. This is important because PyTorch can only perform backpropagation on scalar outputs. An assertion is used to check that y is indeed a scalar, and if it is not, an error is raised stating that y must be a scalar. This verification helps confirm that the computation graph is correctly set up for gradient calculations. We first check whether the input tensor is set to track gradients by looking at its gradient tracking attribute, which confirms that it participates in automatic differentiation. This ensures we will be able to compute gradients with respect to this tensor later. We then print the value of the output using a method that extracts its single numeric value. Doing this lets us verify the result of the computation and confirm that the output is a scalar, which is required before we can safely run the backward operation. We inspect the type of function that created the variable y in the Autograd graph by looking at its gradient function attribute. This attribute stores a reference to the operation that produced y. By checking its type and then reading its name, we can identify exactly which operation created y. This is useful for understanding how y was computed and for debugging the flow of gradients during backpropagation. Calling the backward method on the scalar output starts backpropagation through the computation graph that the automatic differentiation system has built. This triggers PyTorch to calculate how the output changes with respect to the input tensor, assuming gradient tracking is enabled for that input. These computed gradients show how small changes in the input affect the output. This information is essential for optimization tasks, such as adjusting model parameters during training. We print the gradient of the output with respect to the input by reading the gradient attribute of the input tensor. Because this tensor is a leaf node and is marked to require gradients, it collects the gradient values during the backward pass. These values show how small changes in the input would change the scalar output, revealing how sensitive the output is to variations in the input. To create a new tensor from an existing one without tracking gradients, you can use the PyTorch Autograd context manager, which temporarily turns off gradient tracking. This is useful during inference or whenever you do not need gradients. Inside this context, you might define a new tensor by multiplying the original tensor by 5 and then adding 1. The important point is that this new tensor is computed without being added to the automatic differentiation graph, so it does not require gradients and has no associated gradient function. We first check whether the tensor needs gradients by looking at its attribute that indicates if it is part of the computation graph. Because this tensor was created inside a block where gradient tracking is disabled, it should not require gradients, and this check confirms that. We then inspect the attribute that records which function created the tensor in the computation graph. Since gradients were not being tracked when it was computed, this attribute is set to none, confirming that the tensor is not connected to any automatic differentiation functions. Detaching a tensor creates a separate version that is no longer connected to the original computation graph. This detached tensor does not track gradients, so any operations you perform on it are not recorded for gradient calculation. As a result, changes made using the detached tensor do not influence the gradients of the original tensor. This is useful when you want to work with the tensor's values without affecting backpropagation or optimization. We check the detached tensor to confirm that it no longer tracks gradients by verifying that its gradient requirement attribute is set to false. This shows that the detached tensor is no longer part of the automatic differentiation graph. As a result, any operations performed on the detached tensor will not influence the gradient calculations of the original tensor. This verification step ensures the detached tensor is truly independent for further computation. This script shows how PyTorch's automatic differentiation works by building a simple computation graph from a tensor that tracks gradients. It computes a scalar output by combining the first and second elements of the tensor, then confirms that the result is suitable for backpropagation. When the backward operation is called, PyTorch calculates and prints the gradients of the output with respect to the input, revealing how changes in each input element affect the result. The script also demonstrates how to temporarily turn off gradient tracking with a context manager and how to detach a tensor from the graph, which is useful when you want to work with tensor values without influencing gradient calculations. Gradient accumulation essentials. Gradient accumulation is a way to store and build up gradient information over time during training. In PyTorch, each tensor that tracks gradients has a gradient attribute that starts empty, and each backward pass adds new gradient contributions instead of replacing them. If you run several backward passes without clearing these values, the gradients are summed, giving a running total of how each parameter affects different losses. This lets you collect gradient information across multiple cycles before updating the model's parameters, which is useful for managing more complex training setups. When training on very large datasets that do not fit into memory, gradient accumulation lets you effectively use larger batch sizes. Instead of processing a huge batch at once, you handle a few high-resolution samples at a time, compute the loss, and backpropagate to get partial gradients. You do not update the model immediately. Instead, you add these partial gradients together over several small batches. After enough iterations, the accumulated gradients closely approximate those from a single large batch, and you then update the model. This approach makes large batch training possible within real-world memory and computational limits. With gradient accumulation in a dynamic computation graph, a new graph is built for each forward pass to record that pass's operations. When you run backpropagation, gradients are added to the model's parameters and the graph itself is discarded, but the accumulated gradients stay in memory until you clear them. This means you can combine gradient information from several passes, such as multiple mini-batches or tasks, before performing a parameter update. To use this effectively, you must reset gradients deliberately to avoid overly large updates, while using accumulation to smooth out noisy learning signals and make training more stable. Python code. Gradient accumulation essentials. This script introduces the basics of gradient accumulation using very small tensors, so the ideas are easy to see. It is designed as a step-by-step walkthrough where each part builds on the previous one. To follow the explanation, you should run the cells in order while paying attention to the comments that describe what is happening. The command with the exclamation mark installs the PyTorch library along with Torch Vision and Torch Audio. These packages provide tools for working with tensors, neural networks, and audio data in Python. You typically run this command in a terminal or a Jupyter Notebook cell so that all required libraries are installed before running your script. We begin by importing the PyTorch library because it is essential for working with tensors and performing automatic differentiation in deep learning. PyTorch provides the main tools for creating and manipulating tensors, which are the basic data structures used in these models. It also includes an automatic gradient computation feature called Autograd that calculates gradients for us. These gradients are needed to update and optimize model parameters during training. We begin by setting a deterministic random seed using PyTorch's manual seed function. This makes all later random operations produce the same results every time the code is run. Doing this is essential for reproducibility because it allows us to reliably verify, compare, and debug our results across different runs of the program. This code simply checks and reports which version of PyTorch is currently installed. Knowing the exact version helps you confirm compatibility with your project and other libraries. It also tells you what features and behaviors you can expect, since different PyTorch versions may support different capabilities. We create a tensor that holds a single value, the number 2, and set it up to track gradients. Tracking gradients means the system will automatically record how this value is used in computations. This is crucial because it lets us compute gradients with respect to this parameter during backpropagation. Those gradients are then used to update the parameter during optimization in machine learning models. We begin by showing the initial value of the parameter stored in a tensor, so we know its starting point before any operations. We then display its initial gradient, which should be set to none, because no gradient computation or backward pass has been run yet. This simple check establishes a clear baseline that we can compare against after we compute gradients later in the process. We define a helper function called computeLoss that takes a floating point scale value and uses it to compute a simple squared loss. Inside the function, the parameter tensor is multiplied by the scale, and the result is squared to produce the loss. This loss value is then returned. The key idea is that by changing the scale input, we can adjust the loss, which is useful for illustrating how gradient accumulation works. We start by running a forward pass to compute the loss. To do this, we call the loss computation function and give it a scale factor of 1, which in this case does not change the value. The loss is calculated as a simple squared loss based on the parameter tensor. We then store this result in a variable called loss1, so it is ready for the backward pass, where we will compute the gradients. When we call the backward method on the loss, it computes how the loss changes with respect to each parameter, producing the gradient. This gradient is then stored in the gradient attribute of the parameter tensor. Having this gradient available is essential for optimization because it tells us how to adjust the parameter. Using it, we can update the parameter in the direction that reduces the loss. After the first backward pass, the code prints the gradient stored in the parameter's gradient attribute. This gradient is the result of the backward operation, which computes how the loss changes with respect to that parameter. By printing this value, we can see the effect of the backward call and confirm that the gradient has been correctly computed and stored. Here we run a second forward pass by calling the loss computation with a scale of 1/2. This produces a new loss value based on the current parameters. That loss is then used to add more gradient information on top of what was already computed. Using a different scale shows how gradients from multiple loss calculations can be accumulated over several backward passes. When the backward method is called again on a second loss, the new gradient is added to the gradient already stored in each parameter instead of replacing it. This process accumulates gradients over multiple backward passes. It is especially useful for gradient accumulation, where you simulate a larger batch size by running several smaller batches, summing their gradients, and only then updating the model parameters. After the second backward pass, the code prints the current gradient stored in the parameter to show how it has changed. This printed value reflects the accumulated contributions from both backward passes. By examining this updated gradient, you can confirm that gradient accumulation is functioning correctly. We manually compute the expected accumulated gradient by combining two terms, 2 times 1 squared times the parameter value without gradient tracking, and 2 times 0.5 squared times the same parameter value without gradient tracking. This gives us a single expected gradient value. We then compare this manual result with the gradient produced by the backward passes. If they match, it confirms that the accumulated gradient from the backward computations is correct. We print the expected accumulated gradient so we can easily compare it with the actual gradient produced by the model. This comparison helps confirm that gradient accumulation is behaving correctly. The expected gradient comes from the manual calculation we performed earlier, and we use a method that extracts its numeric value so it can be clearly displayed. Before starting a new round of gradient accumulation, You must reset the gradients to 0 so that values from earlier computations do not carry over. Clearing the gradient values on each parameter removes any leftover information from previous steps. This reset is essential to keep gradient calculations accurate and to ensure that each training iteration reflects only the current batch of computations. We verify that the gradient has been reset by printing the current gradient value for the parameter. This check confirms that any previous gradient information has been cleared. Seeing a value of 0 indicates that the reset was successful. This ensures that future operations start accumulating gradients from a clean state. At the end of the script, a final message is printed to confirm that the gradient accumulation demonstration has finished. This message indicates that all steps have run as intended. It serves as a simple check that the script completed without issues. Hearing this message tells you the example executed successfully from start to finish. This script shows how gradient accumulation works in PyTorch. It starts by fixing the random seed, then creates a parameter with gradient tracking and computes a simple squared loss. After a backward pass to get the gradient, it computes a second loss with half the scale and adds its gradient to the existing one, then checks that the accumulated gradient matches the expected manual value. Finally, it resets the gradient to 0 and confirms the reset. This demonstrates how gradients can be built up over multiple backward passes before being cleared, which is useful in training scenarios like mini-batches. Working with gradients. Controlling requires grad. In automatic differentiation, not every tensor needs to participate in gradient calculations. The requires grad flag marks which tensor should be tracked for gradients and which act as constants or intermediate values. You can think of it as tagging certain values so the system remembers how they were produced and can later compute their gradients. For example, in a housing price model, you want gradients for parameters like weights and biases, but not for input features such as square footage. Setting this flag correctly keeps the computation graph efficient and focused only on what is needed for learning. When you work with tensors that require gradients, every operation on them is tracked and linked into a computation graph that Autograd uses to compute derivatives. If tensors do not need gradients, or if gradient tracking is turned off, they are excluded from this graph. This is helpful during data preprocessing, such as normalizing images or tokenizing text where gradients are unnecessary. By making only the model parameters require gradients, you keep the computation graph smaller and more focused on learning. This makes training more efficient because the graph starts at the parameters instead of the raw data. When working with tensors, you should carefully choose which ones track gradients, because this affects both speed and memory use. Every tensor that tracks gradients must store extra information about how it was created, which becomes costly in large tasks like training language models or handling high-resolution images. If non-essential computations, such as diagnostic metrics, are allowed to require gradients, they can unnecessarily grow the computation graph and slow everything down. By limiting gradient tracking to the parameters and loss functions that matter for learning, you keep the graph efficient, avoid unwanted gradient propagation, and maintain a clear understanding of the computation. Python code. Controlling requires grad. This script gives a clear, simple introduction to how and why you control the requires grad setting when working with gradients. It uses straightforward examples to show how gradient tracking behaves in different situations. You are encouraged to run the cells one at a time and read the printed messages to see how changing this setting affects gradient computation. By following along step by step, you can build an intuitive understanding of basic gradient tracking. In some environments, the PyTorch library is not installed by default, which can cause an import error when you try to use it. If this happens, you should install PyTorch along with its related packages for vision and audio. You can do this by enabling the provided installation command in your setup. Once installed, you will have the necessary tools for tensor operations and audio processing in PyTorch. We begin by importing the Torch library, which is the main tool for working with tensors in this context. Torch lets us create and manipulate tensors efficiently and also supports automatic differentiation. This means it can track and compute gradients, which is essential for training neural networks and other machine learning models. In short, importing Torch provides the core functionality needed for tensor operations and gradient-based learning. We begin by checking and printing the installed PyTorch version. This simple step confirms which version of the library the environment is using. Knowing the exact version helps verify compatibility and clarifies which features and behaviors are available for the work that follows. We create a tensor using the Torch library that holds the values 2 and 3, and we do not enable gradient tracking for it. This means that when we perform operations with this tensor, the system will not compute gradients with respect to its values. Skipping gradient tracking reduces overhead and is appropriate when the tensor represents input data rather than model parameters we want to optimize. We create a tensor called W-param, a small multi-dimensional array initialized with the values 1.5 and -0.5, and we turn on gradient tracking for it. Enabling gradient tracking means that any operations using this tensor are recorded by PyTorch's automatic differentiation system. Later, this allows us to compute gradients with respect to these values. This is essential in optimization tasks like training machine learning models, where parameters must be updated based on their gradients. We first check whether the input tensor has gradient tracking enabled by looking at its gradient requirement attribute, which tells us if gradients will be computed for it during backpropagation. We then do the same check for the parameter tensor to confirm its gradient tracking status. This process shows which tensors will receive gradients and helps verify that the parameter tensor is correctly set up for learning. We are computing a simple linear combination using two tensors. Each element of the input tensor is multiplied by the corresponding element of the parameter tensor, and all these products are then added together. This produces a single scalar value as the output. Such linear combinations are a basic operation in many machine learning models, where they are used to form predictions or intermediate computed values. Calling the backward method on the output tensor starts the process of computing gradients. This operation finds how the output changes with respect to the parameter tensor, which has gradient tracking turned on. These computed gradients are then used to update the parameters during optimization in machine learning models. We are looking at the gradient stored on the parameter tensor called W-param to see the result of the backward pass. The backward pass computes how the output changes with respect to this parameter. This gradient tells us how sensitive the output is to changes in W-param. It is then used in optimization methods such as gradient descent to update the parameter values and improve the model. We reset the gradients of the parameter tensor to 0 so that any previously accumulated values are cleared out. This ensures that each new backward pass starts from a clean state. Doing this is essential in iterative optimization, such as training a neural network, because it prevents gradients from different training steps from being mixed together and corrupting the update. We begin by creating a tensor whose value is 10, but we do not enable gradient tracking for it yet. Without gradient tracking, operations that use this tensor will not produce gradients automatically. This behavior is useful because it lets us control exactly when and where gradients are computed. In practice, we can later choose to enable gradient tracking only for the parts of the computation where we need it. We enable gradient tracking on the tensor called scale by using the PyTorch method that sets the requires gradient flag. This tells PyTorch to record all operations applied to that tensor. As a result, the tensor becomes part of the automatic differentiation system. This is essential for computing gradients during backpropagation in neural networks. We check whether the tensor called scale is set up to track gradients by looking at its requires grad attribute. This tells us if operations involving this tensor will be recorded for gradient computation. Knowing this is important because gradient tracking is essential for optimization steps in machine learning models. We create a new computation by multiplying the scale tensor with the sum of the element-wise product of the data tensor and the parameter tensor. This combines both tensors into a single operation. Because both tensors are set up for gradient tracking, we can later compute gradients with respect to them. This is important for optimization and learning in gradient-based methods. When we call the backward method on the result tensor, the system computes gradients for all tensors that were involved in producing that result and have gradient tracking turned on. These gradients describe how small changes in each tensor would change the final result. The values are stored for later use, which is essential in optimization tasks. By knowing how sensitive the result is to each parameter, we can adjust those parameters to reduce error. After computing the gradients, we display the gradient of the parameter tensor to see how changes in each of its elements affect the output. We then display the gradient of the scale tensor to see how changes in the scale influence the output. Together, these gradients show how sensitive the output is to variations in these tensors and help us understand their impact on the model's behavior. In PyTorch, you can use a special no-gradient context to temporarily turn off gradient tracking when it is not needed. This makes computations more efficient by saving memory and reducing processing time. Inside this context, you might compute a prediction by multiplying the input data and a parameter element by element, and then summing the result. The key idea is that this prediction is calculated without storing any information for gradient computation, which is useful when you only care about the output and not about updating the model with gradients. We check whether the prediction tensor has gradient tracking enabled, because it was created inside a block where gradient tracking was turned off. By printing its gradient requirement attribute, we verify that gradient tracking is indeed disabled for this prediction. This confirmation matters because it ensures that the system does not waste computational resources tracking gradients when they are not needed. We check whether the parameter tensor still has gradient tracking enabled. This matters because even if we perform some operations without tracking gradients, such as inside a no-gradient context, the parameter itself should keep its ability to track gradients. By confirming this, we ensure that any later operations involving this parameter can still compute gradients when needed for learning or optimization. This script shows how to manage gradient tracking in PyTorch. It first creates one tensor without gradient tracking and another with tracking enabled, then combines them so that gradients are computed only for the parameter tensor. After clearing those gradients, it creates a new tensor and turns on gradient tracking using the requires grad setting, performs another computation, and computes gradients again. The script also demonstrates how to temporarily turn off gradient tracking with a no-grad context for more efficient inference, while printing out which tensors are being tracked at each stage to illustrate how PyTorch handles gradients in different situations. Understanding backward and grad. During the backward pass, the system traces the chain of operations in reverse, passing gradient information from the final result back to earlier tensors. As tensors track both their values and how they were computed, calling the backward operation on a scalar output tells the system to measure how sensitive that result is to each earlier tensor. Using the chain rule, it automatically fills the gradient attribute of every relevant tensor with the correct derivatives. This allows you to compute a loss, call backward once, and obtain all the gradients needed to update your model parameters without doing the calculus yourself. The grad attribute of a tensor stores the gradient computed during the backward pass, but it remains empty until you run backward on some output that depends on that tensor. After the backward step, each parameter tensor's grad attribute contains a gradient tensor with the same shape, showing how small changes in each element would affect the final output. For example, in a model that predicts sales from advertising spend, calling backward on the loss fills each weight's grad attribute with values that indicate how changing that weight would change the loss. By examining these gradients, you can see which parameters most strongly influence the predictions and in which direction they push the output. The backward operation is not limited to simple cases, and its behavior depends on how your computations are set up. When your output is a tensor with many elements, you must decide how to combine those elements before gradients can flow backward. In more complex workflows, calling backward multiple times will add to the existing gradient values instead of replacing them, which is useful when aggregating over many batches. But it requires you to clear gradients when needed. This accumulation means you must be careful about when you inspect gradients and how you interpret them. By viewing backward as the trigger that computes gradients and the gradient attribute as the place where they are stored, you can use them effectively in both simple and complex models. Python code, understanding backward and grad. This script introduces the basics of backward passes and gradient computation. It uses very small tensors, so you can clearly see how the gradients are formed. To get the most out of it, run the cells in order while following along with the explanations. To work with PyTorch, you may need to install it along with the Torch Vision and Torch Audio libraries. This step is important if they are not already present in your environment. Together, these libraries provide the core tools for handling tensors and for processing visual and audio data in PyTorch. We begin by importing the PyTorch library, which gives us tools for working with tensors and automatic differentiation. These tools are essential for building and training neural networks. Automatic differentiation lets us compute gradients without doing the math by hand, which is crucial for optimization during training. In short, PyTorch handles the low-level calculations so we can focus on designing and improving our models. We begin by printing the version of PyTorch we are using. Knowing the exact version is important because different versions can change how certain features work or how fast they run. This helps us make sure that any results we obtain can be reproduced later under the same conditions. We begin by creating a tensor that holds a single value, the number 2, and we turn on gradient tracking for it. With gradient tracking enabled, PyTorch's automatic differentiation system records all operations that use this tensor. This recording allows us to compute gradients later, which tell us how changes in the input affect the output. This capability is essential for optimization tasks, where we need these gradients to update parameters and improve model performance. We print the tensor to confirm it is set up correctly, then verify that it is a leaf tensor, meaning it is a starting point in the computation graph. We also check that gradient tracking is enabled for it. This setup is important because it ensures that any later operations involving this tensor are recorded for automatic differentiation. As a result, we will be able to compute gradients with respect to this tensor during backpropagation. We define a simple mathematical expression that depends on a tensor called x, where y is given by x squared plus 3 times x. This means the value of y changes whenever x changes. Setting up this dependency is important because it lets us use PyTorch's automatic differentiation to compute how y changes with respect to x. In other words, it allows PyTorch to automatically calculate the gradient of y with respect to x. At this point, we display the value of the output before running the backward operation. This output depends on the input through the expression where y equals x squared plus 3 times x. Printing this value lets us confirm that the computation produced the expected result. Once we have verified the output, we can then safely proceed to calculate the gradient. We check whether the tensor y is a leaf tensor and whether it has an associated gradient function. A leaf tensor is one that is created directly by the user, not produced as the result of an operation. Because y comes from a computation involving another tensor, it is not a leaf tensor. The fact that y has a gradient function tells us it was created by an operation that supports automatic differentiation, so its operations can be tracked for computing gradients. Before running the backward operation, we first inspect the gradient stored for x to make sure it is empty. By printing this gradient beforehand, we verify that it is set to none, meaning no gradient has been calculated yet. This clean starting point lets us clearly see the effect of the backward computation on x's gradient. When we call the backward method on the scalar output y, PyTorch's automatic differentiation engine computes how y changes with respect to x. It calculates the derivative of y with respect to x and stores this gradient in the grad attribute of x. This tells us how small changes in x will affect the output y. Understanding this relationship is fundamental for optimization and training neural networks. When you call the backward function on the output y, PyTorch's automatic differentiation system computes how y changes with respect to x. It then stores this result, the gradient of y with respect to x, in the grad attribute of x. In other words, after backpropagation, x's grad value holds the derivative that was just calculated. We manually compute the derivative of the function with respect to x, so we can compare it to the result from PyTorch's automatic differentiation. To do this, we first detach x from the computation graph, so it no longer tracks gradients. We then multiply this detached value by 2 and add 3. This manual result gives us the expected gradient, which we can directly compare to the gradient produced by PyTorch's Autograd system. We compare the gradient produced by PyTorch's automatic differentiation with a gradient we compute by hand. The manual gradient uses the expression 2 times x plus 3, where x is detached from the computation graph so its operations are not tracked. By checking that the Autograd result matches this manual value, we confirm that PyTorch is computing the correct gradient. Before running another backward pass, we reset the gradient of x to 0. This is necessary because in PyTorch, gradients are added to the existing values by default. Clearing them first makes sure the next backward pass computes new gradients from scratch. This prevents old gradient values from interfering with the current calculation. We create a tensor containing the values 1, 2, and 3, and turn on gradient tracking for it. By enabling this option, the system will record operations involving these values. This makes it possible to compute gradients with respect to the tensor later in the code. In other words, we prepare the tensor so it can participate in automatic differentiation. We first check and report the shape of the tensor called values. This is important because the shape tells us how many elements it has and how they are arranged. By knowing this, we can better predict how the backward operation will behave. In particular, it helps us anticipate the structure of the gradients that will be computed for that tensor. We compute the mean of the tensor called values, which reduces all its elements to a single averaged number. This step is important because it turns the multi-element tensor into a single scalar. Having a scalar output is necessary for the backward function to properly compute gradients during automatic differentiation. We call the backward method on the mean output to compute how the mean depends on each element of the values tensor. This calculates the gradient of the mean with respect to those values and stores the result in the gradient attribute of the values. By doing this, we can see how changes in each input value influence the overall mean, which is crucial for understanding input contributions during optimization. After we call the backward function on the mean of a tensor, we can inspect the gradients stored in the original values. These gradients show how the mean operation depends on each individual element. By examining them, we see exactly how the mean distributes its influence across the tensor. This provides a clear view of how gradients are computed for the mean during backpropagation. This code example shows that PyTorch's automatic differentiation correctly computes the gradient of the mean function. For a tensor with 3 elements, the derivative of the mean with respect to each element is 1 divided by 3. The printed output confirms that each element's gradient is exactly 1/3. This match between the expected derivative and the computed gradient verifies that the Autograd system is working as intended. This script introduces the basics of PyTorch's automatic differentiation system. It creates a tensor with gradient tracking, performs a simple computation, and shows that the gradient is initially empty. After calling the backward function, the correct gradient is computed and stored, matching the expected derivative. The script then resets the gradient and repeats the process with a tensor containing multiple elements, using the mean so the output is a single value. The resulting gradients for each element confirm the expected derivative of 1/3, illustrating how Autograd handles multi-element tensors. Resetting gradients safely. When working with gradients, you must reset them between computations so they do not accumulate. In training workflows, each new computation adds its gradients to the existing ones, so failing to clear them gives you a sum of past values instead of just the latest result. This behavior can make your measurements meaningless and your model updates incorrect. Understanding that gradients persist and add up by default explains why regularly resetting them is essential for accurate and interpretable outcomes. Resetting gradients is essential for keeping the learning process accurate. During training, such as when predicting housing prices, each gradient should represent only the current batch of data. If you do not clear the gradients first, they accumulate information from previous batches and produce incorrect updates. This can make training unstable and harder to debug. By resetting gradients before each computation, you ensure that model updates are based on fresh, relevant information, and that analysis of the training process remains reliable. Resetting gradients is important when experimenting and tuning machine learning models because it lets you accurately see how changes in parameters affect the outputs. If you do not clear gradients consistently, they can accumulate, making large gradients look like instability and small ones look like underfitting, even when that is not true. In more complex workflows, you may choose to accumulate gradients on purpose and then reset them at specific times. By managing when gradients are cleared, you keep control over your computations, reduce bugs, and maintain a clean, reliable learning process. Python code, resetting gradients safely. This material explains how to safely reset gradients when working with PyTorch. It uses simple tensor operations on scalar values to illustrate the process. The focus is on how the requires grad setting controls gradient tracking, how the backward pass computes gradients, and how the grad attribute stores those results. Overall, it highlights the correct way to manage gradients during automatic differentiation. To use PyTorch in your environment, you may need to install it first. This is typically done with a package manager command that installs PyTorch together with the TorVision and TorAudio libraries. These additional libraries are commonly used for working with image and audio data. The installation command is often run in a quiet mode, so it hides unnecessary output and keeps the process easier to follow. We begin by importing the Torch library, which is the core of PyTorch for working with tensors and automatic differentiation. This library lets us perform complex tensor operations and efficiently compute gradients. By bringing Torch into our script, we gain the essential tools needed to build and train neural networks. This import is therefore a necessary first step for the tasks we will carry out next. We begin by printing the version of PyTorch that is currently installed. This quick check confirms which release of the library we are using. Knowing the exact version helps us ensure compatibility with our code and correctly interpret any version-specific features or behaviors that appear when the script runs. We begin by creating a single numeric parameter and enabling gradient tracking for it using PyTorch tensors. Turning on gradient tracking tells PyTorch to record all operations applied to this value. Later, PyTorch can use this record to automatically compute gradients with respect to the parameter. This capability is essential for optimization, where we repeatedly update parameters based on their gradients to improve performance. We verify that the tensor called weight is a scalar parameter by checking its shape. In PyTorch, a scalar tensor has an empty shape with no dimensions. This tells us that weight represents a single value rather than an array or matrix. Confirming this is important because the operations we plan to perform assume that weight is just one number. We set up a simple target value for this example by creating a PyTorch tensor that holds the number 10. This target acts as a fixed reference point that we compare our model's outputs against during calculations. Because it is only used as a constant for comparison and not updated through learning, it does not need gradient tracking. We check that the target tensor is compatible with the prediction tensor by confirming that its shape indicates a single scalar value. This assertion ensures both tensors match in the way they are structured. By doing this, we can safely perform later operations that rely on the target and prediction having consistent shapes. In this step, we make a simple prediction by multiplying the weight, which is a single scalar parameter, by the value 3. This is a basic linear transformation of the weight. It does not involve any complex operations, but it prepares the result for later steps such as computing the loss. Squared error loss is found by subtracting the target value from the prediction and then squaring the result. This gives a non-negative measure of how far the prediction is from the true value. It is crucial because it quantifies prediction error and serves as the basis for computing gradients during backpropagation. Backpropagation is used to compute how the loss changes with respect to a weight. This calculation updates the gradient stored in the weight tensor. The gradient tells us how a small change in the weight will affect the loss. With this information, we can adjust the weight in the direction that reduces the loss, which is the core of the optimization process. After running backpropagation for the first time, we print the gradient of the weight tensor. This gradient is the computed value that tells us how the weight parameter should change to reduce the loss. Examining it is important because it shows both the direction and magnitude of the needed adjustment. In short, the printed gradient directly guides how the optimizer will update that weight during training. We save the current gradient of the weight tensor in a variable called first gradient. This stored value serves as a reference point after the first backpropagation step. By keeping it, we can later compare it with new gradient values. This helps us observe how the gradients change as we perform additional operations or training steps. We now make another prediction using the current value of the weight without clearing the gradients. This means the same weight value is reused, and the prediction is again found by multiplying the weight by 3, just as before. Doing this shows that when we run another backward pass without resetting, the gradients from this new prediction are added to the existing gradients. In other words, this step illustrates how gradients accumulate if they are not cleared between backward passes. We now compute an updated loss by taking the new prediction, subtracting the target value, and squaring that difference. This is the same type of calculation we used before, but applied to the revised prediction. Doing this lets us compare the new loss to the original one and see how it changed after the update. When we call the backward method again on a second loss, we add the new gradient to the gradient that is already stored in the weights gradient attribute. This process is called gradient accumulation. It allows us to combine gradient information from multiple stacks or batches before we update the model's parameters. This is useful when we want to simulate a larger batch size or smooth out updates over several iterations. We print the gradient of the weight after running backpropagation a second time to show that the gradient value has accumulated. The new gradient is added to the one computed in the previous pass, so the total grows instead of being replaced. This happens because we did not reset the gradients between the two backpropagation steps. It demonstrates that by default, gradients build up over multiple passes unless they are explicitly cleared. We verify that gradient accumulation is working by checking whether the accumulated gradient is roughly twice the initial gradient. To do this, we compare the current gradient to the first gradient scaled by about 1.9. If these values are close, it indicates that multiple backward passes have correctly added up the gradients as expected in this setup. To safely reset the gradients of a weight tensor, we set its gradient values to 0 using the appropriate reset method. This clears any gradients that were accumulated during previous backward passes. Doing so ensures that each new gradient calculation starts from a clean state. This step is essential in iterative optimization, such as training neural networks, to avoid incorrect gradient accumulation and prevent erroneous weight updates. We verify that the gradients have been cleared by checking the current gradient value of the weight tensor. This check confirms that the gradient reset step worked as intended. When the operation is successful, the printed gradient value is 0. Seeing this 0 value tells us that the gradients have been properly removed and the model is ready for the next update. After clearing the gradients, we compute a new prediction by multiplying the weight by 3. This reset is important because it gives the model a fresh gradient state. It prevents leftover gradients from earlier steps from influencing the current prediction. As a result, we can observe how the model behaves based only on the most recent update. After clearing the previous gradients, we compute a new loss using the latest prediction. We do this by taking the difference between the prediction and the target and then squaring that difference to get the squared error loss. This ensures that the loss and the gradients we compute next come only from the current state of the model. As a result, the upcoming backpropagation step is based on fresh, accurate information without any leftover influence from earlier updates. We now run backpropagation again on the third loss value, but only after resetting the gradients to 0. This step recomputes the gradient of the loss with respect to the weight parameter from scratch. Clearing the old gradients ensures that the new gradient is not contaminated by any previous calculations. This allows us to check that the gradient we obtain matches what we expect from a single, isolated backward pass. We now print the gradient of the weight after clearing the previous gradients and running backpropagation again. This lets us see the gradient value as it appears after a single backward pass. By comparing it to the original gradient, we confirm that resetting the gradients worked properly. This also shows that the new computation is consistent with the initial gradient calculation. We check that the new gradient matches the original by comparing their difference to a very small threshold, 1 times 10 to the minus 6. If the absolute difference is smaller than this value, we treat the gradients as effectively the same. This confirms that clearing the gradients and recomputing them produces consistent results. In turn, this helps ensure the reliability and integrity of our gradient calculations. This script shows how gradient management works in PyTorch and why resetting gradients is important. It starts with a scalar parameter that tracks gradients, computes a prediction and loss, and then runs backpropagation to obtain the gradient. Without clearing the gradient, it performs another prediction and loss, demonstrating that the new gradient adds to the old one and effectively doubles. The script then resets the gradient to 0, runs backpropagation again, and confirms that the gradient now matches the original single-step value. This illustrates that gradients accumulate by default and must be cleared between steps to keep optimization consistent and avoid unintended accumulation. Controlling autograd gradients. No-grad context. A no-gradient context is a temporary mode where automatic differentiation stops tracking operations. Inside this context, tensor operations are not recorded, no computation graph is built, and no gradients are produced during backpropagation. This is especially useful for tasks like model evaluation or logging, where you want to use the model's outputs without updating its parameters. By clearly separating these phases, you keep gradient tracking focused only on computations that matter for learning. In a large recommendation system, training and inference have different needs. During training, the system must track every operation so gradients can update the model's parameters. During inference, when it is only generating recommendations, gradients are not needed. If gradient tracking is accidentally left on, the system builds unnecessary computation graphs and wastes resources. Using a no-gradient context during inference keeps operations read-only for learning and makes the system more efficient and responsive. When monitoring a model during training or computing extra statistics, it is important to use a context where gradients are not tracked. This keeps validation, visualizations, and metrics like accuracy and loss from affecting the computation graph. If gradient tracking stays on, the graph can grow unnecessarily and lead to bugs or memory problems. Treat these evaluation steps as purely observational, so the training loop remains clean, efficient, and clearly separated from how the model applies what it has learned. Python code, no-grad context. This lesson demonstrates how the no-gradient context in PyTorch works. It compares what happens to gradients when this context is used and when it is not. The focus is on simple tensors rather than full neural network models, so you can clearly see the effect on gradient computation. By the end, you should understand how this context controls whether gradients are tracked. This line includes a comment explaining that if the PyTorch library is not already installed, you can remove the comment marker to run the install command. This helps make sure the required library is available so the script can run correctly. Including such optional installation instructions is a common practice when sharing code that depends on external libraries, since other users may not have the same environment set up. We begin by importing the Torch library, which is the main tool for working with tensors and automatic differentiation in this context. Torch lets us create and manipulate tensors and efficiently perform numerical computations. It also computes gradients, which are essential for optimization and training machine learning models. By importing Torch, we gain access to all these capabilities in a single powerful framework. We set a manual seed in the Torch library, using 0 as the seed value, to make all random operations produce the same results every time the code runs. This makes the program's behavior deterministic instead of changing from run to run. Deterministic behavior is important for reproducibility, so we can reliably repeat experiments, and for debugging, so we can track down and compare results under consistent conditions. We create a tensor with the value 2 and enable gradient tracking so PyTorch can perform automatic differentiation. With gradient tracking turned on, every operation that uses this tensor is recorded. This record allows PyTorch to compute derivatives later. Such derivatives are essential for optimization tasks, where we need to understand how small changes in the input affect the output. We print a message to check whether the tensor has gradient tracking turned on. This tells us if it is prepared to compute gradients during backpropagation. Knowing this is essential because gradient computation is what allows us to perform optimization in machine learning models. We define a simple mathematical expression using a tensor called x, where y is given by x cubed plus 2 times x. This setup is important because it lets us see how changes in x influence the value of y. By expressing y in this way, we make it possible for automatic differentiation tools to compute the gradient of y with respect to x. Computing this gradient is a fundamental step in many optimization and learning algorithms. Here, calling the backward method on the output tells PyTorch to compute how that output changes with respect to the input. This uses automatic differentiation to find the derivative of the output in terms of the input. Because the input was created with gradient tracking turned on, this call fills its gradient attribute with the computed value. This stored gradient is then used in optimization to update parameters based on how they affect the output. We now display the gradient of the output with respect to the input, which has been computed automatically by the differentiation system. To do this, we read the stored gradient value from the input variable and convert it into a regular Python number, so it can be printed. This confirms that gradient tracking is functioning properly and shows how a small change in the input would affect the output. We reset the gradient stored for the tensor x to avoid unwanted accumulation from earlier computations. This is done by calling the method that clears its gradient values. Removing old gradients ensures they do not interfere with new calculations, and that each training step starts with a clean slate for gradient updates. Inside a no-grad context, gradient tracking is turned off, so operations are not recorded for automatic differentiation. In this mode, you can compute a new tensor, for example, by cubing a value and adding twice the original value, and the result will not store any gradient information. This is useful when you want to perform calculations that should not affect the gradient history, such as during evaluation or certain preprocessing steps. Inside the no-gradient context, we perform the same computation as before, raising the tensor x to the third power and adding twice x, and store the result in a new tensor. We then print this result to show that the operation still produces a valid tensor value. This demonstrates that disabling gradient tracking only affects the recording of gradients, not the actual numerical computation. We check whether a tensor created inside a no-gradient context is tracking gradients by looking at its requires gradient property. Because this tensor was computed within a no-gradient block, it is not supposed to track gradients. The check confirms this behavior, since the property is set to false. This verifies that operations inside the no-gradient region are excluded from gradient computation. This example shows what happens when you try to run backpropagation on a tensor that was created inside a no-gradient context. Because gradient tracking was disabled when the tensor was computed, it does not store any gradient information. As a result, calling the backward method on it triggers a runtime error. The code catches this error and prints a message explaining that the backward operation failed and that the exception is a runtime error. This demonstrates that operations performed inside a no-gradient context do not support gradient computation. We print the gradient of x after leaving the no-grad block to verify that it has not changed. This confirms that the no-grad context successfully blocked any gradient updates while it was active. To read the gradient as a simple number, we use a method that extracts the scalar value from the tensor. This script shows how PyTorch's no-grad context controls gradient tracking. It first creates a tensor with gradients enabled, performs a simple computation, and successfully computes and prints the gradient, demonstrating the default tracking behavior. After clearing the gradient, it repeats the same computation inside a no-grad context, where gradients are not tracked, and calling backward fails as expected. Finally, it confirms that the original tensor's gradient is unchanged by the operations inside the no-grad block, illustrating how this context lets you run computations without affecting gradient calculations. Detach and in-place operations. Detach is a tool for controlling gradient flow in automatic differentiation. When you detach a tensor, you tell the system to treat it as a constant, even if it originally required gradients. The detached tensor keeps the same values but is removed from the computation graph, so it no longer influences earlier gradient calculations. This is useful when you want to fix a model's output as a target or stop gradients in certain algorithms, such as in reinforcement learning. By choosing where to detach, you decide which parameters are updated during optimization and which remain unchanged. In-place operations directly change a tensor's data, which can interfere with the Autograd system if that tensor is part of an active computation graph. To avoid breaking gradient calculations, you can first detach the tensor so it is no longer tracked, and then safely apply in-place modifications. However, if you still need the original tensor for gradient computation, you should not perform in-place changes that alter values required for those gradients. In practice, reserve in-place operations for tensors that are detached, not needed for gradients, or used in ways that do not conflict with Autograd's tracking. When working with advanced workflows, it is important to understand how detach and in-place operations interact. You can safely compute features with gradient tracking, then detach them and use in-place updates to maintain a smooth buffer, because that detached buffer is no longer part of the gradient path. In contrast, performing in-place updates directly on tensors that are still tracked by the automatic differentiation system can cause errors or incorrect gradients. Using detach carefully before in-place updates keeps your computations both correct and efficient. Python code, detach and in-place operations. This material introduces how detach and in-place operations work in PyTorch's automatic differentiation system. It uses simple tensor examples to show how to control whether gradients are tracked or not. The focus is on using detach to safely stop gradient flow when needed, and understanding how in-place changes can affect gradient computation. Overall, it highlights safe practices for managing gradients and in-place behavior when working with Autograd. The script begins by installing PyTorch along with its vision and audio libraries to make sure they are available in the environment. It uses a specific package index that provides CPU-only versions of these libraries. This installation step is essential because the rest of the script depends on PyTorch for working with tensors and using automatic differentiation. We begin by importing the Torch library, which is the main tool for working with tensors in this environment. Torch lets us create and manipulate tensors efficiently, and it also supports automatic differentiation. This means it can build and manage computation graphs that track operations on tensors. These graphs are essential for computing gradients, which are used in gradient-based optimization methods during model training. We start by setting a fixed random seed using PyTorch's manual seed function so that any random operations in our code produce the same results every time we run it. This makes our experiments reproducible, meaning we can reliably repeat them and get identical outcomes. Reproducibility is essential for comparing results, verifying findings, and debugging models or training procedures. We begin by printing the version of PyTorch that is currently installed. This helps confirm that the environment is set up as expected and that we are using the intended release of the library. Knowing the exact version is important because different versions can change features or behavior. By checking it up front, we make later debugging and compatibility checks much easier. We create a tensor with the values 2.0 and 3.0 and enable it to track gradients. Tracking gradients means the tensor records the operations applied to it so that automatic differentiation can be performed. This capability is essential in tasks like training neural networks, where we need gradients to update model parameters during optimization. We begin by checking that the tensor has the correct shape before using it. An assertion is used to confirm that it is one-dimensional and contains exactly two elements. If this condition is not satisfied, an error message explains that the input tensor must have a shape of 2. This validation step ensures that all later operations are applied to data in the expected format. In this step, we build a simple computation graph by taking an input tensor and squaring each of its elements to produce a new tensor. This defines a clear relationship between the input and the output within the model. Establishing this relationship is important because it sets up the structure needed for later operations that will compute gradients based on how the output depends on the input. We compute the loss by adding all the values in the output tensor, which collapses it into a single scalar. This scalar loss is important because backpropagation requires a single value to measure how well the model is performing. Once we have this scalar, we can calculate gradients with respect to the input tensor and update the model parameters. This process enables effective optimization in neural networks. In this part of the code, we run backpropagation by calling the backward method on the loss. This method walks through the computation graph created during the forward pass and calculates how the loss changes with respect to each tensor that is set to require gradients. As a result, the gradient attribute of the tensor x is filled with these computed values, showing how changes in x would affect the loss. We first print the gradients of the tensor before doing any detach operations, so we can see their initial values from backpropagation. This gives us a clear baseline for how the gradients look in the original computational graph. Later, when we detach and modify the tensor, we can compare the new gradients to this baseline. This comparison helps confirm that our detach and modification steps are affecting the computational graph as intended. To stop tracking gradients for a tensor, you create a detached version of it using the detach operation. This produces a new tensor that shares the same underlying data as the original, but no longer records operations for gradient computation. As a result, you can safely perform further calculations on the detached tensor without affecting the gradients of the original one. We detach the tensor to check that it still shares the same underlying data as the original, but no longer tracks gradients. By examining its requires gradient flag, we see that it is set to false, which confirms it is excluded from the automatic differentiation process. As a result, any operations performed on the detached tensor will not influence gradient calculations for the original tensor. In this example, we modify a tensor that has been detached from the computation graph using an in-place add operation that increases each element by 1. This changes the data directly in memory without creating a new tensor, which is more efficient. Because the tensor is detached and no longer tracks gradients, This in-place update does not affect gradient calculations in the original computation graph. After we perform an in-place operation on the detached tensor, we print the original tensor and see that its values have not changed. This shows that modifying the detached tensor does not affect the original tensor. We then print the detached tensor to see the result of the in-place addition. Together, these steps demonstrate that a detached tensor can be updated independently, without altering the computation graph or the gradients of the original tensor. Before starting a new backward pass, we need to clear any gradients that were previously stored in the tensor. We do this by resetting the gradient attribute to 0. This prevents old gradient values from carrying over and affecting the new computation. As a result, the gradients we calculate for the next set of operations are accurate and based only on the current pass. We recompute the loss using the original tensor to make sure the gradients do not depend on any earlier operations. To do this, we square each element of the tensor and sum these values to obtain a single scalar loss. This fresh calculation is important because it lets us verify that the gradients from later steps are not influenced by changes made to any detached versions of the tensor. We run backpropagation again to update the gradients using the original tensor x. After clearing the previous gradients, this recalculation ensures that any modifications made to the detached tensor do not influence the gradient computation for x. This separation is important because it preserves the correct gradient values and maintains the integrity of the training process. After running a second backward pass, we print the gradients for the original tensor and see that they are unchanged. This shows that gradient computation is always based on the original tensor, not on any detached copy. As a result, any in-place modifications made to the detached version do not affect the gradients. This confirms the independence of the gradient calculation from operations performed on the detached tensor. We start by showing an unsafe example of trying to change a tensor directly while it is being tracked by the automatic differentiation system. In a protected block of code, we create a new tensor by multiplying the original tensor by 2. This new tensor now depends on the original one, forming part of a computation graph. With this setup, we can examine what happens when we attempt in-place modifications on tensors that participate in this graph, and why such operations can be problematic. When you perform an in-place operation on a tensor that comes from another tensor and is still tracking gradients, you directly change the data that the automatic differentiation system depends on. For example, adding 1 to every element of such a tensor in place modifies its values without creating a new tensor. This can confuse the gradient tracking process and lead to incorrect derivative calculations. Therefore, in-place operations on tensors that require gradients are risky and should generally be avoided. The code tries to print a tensor after applying an in-place modification to it, and this is done inside a try block to safely handle errors. If the in-place change, which depends on another tensor, works correctly, it prints a message saying the operation succeeded. If a runtime error occurs because automatic differentiation does not allow this kind of in-place update, the code catches the error instead. It then prints a message that a runtime error happened and shows the first line of the error message to explain what went wrong. At the end, the script prints the current values of the tensor to confirm that it has not been altered. This shows that even after working with detached versions or attempting unsafe in-place changes, the original tensor's data and gradient information stay intact. Verifying this is important for maintaining the correctness and reliability of the tensor's values and gradients throughout the computation process. This script illustrates how PyTorch's automatic differentiation handles detaching tensors and using in-place operations. It begins with a tensor that tracks gradients, computes a simple loss by squaring and summing its values, and then performs backpropagation to obtain gradients. The tensor is then detached, so it no longer tracks gradients, and an in-place addition is applied to this detached version, which does not change the original tensor's gradients. After clearing and recomputing the gradients, the script confirms they remain correct. Finally, it attempts an unsafe in-place change on a gradient tracking tensor, which raises a runtime error and highlights the need for careful management of in-place operations when using Autograd. Memory and speed. Automatic differentiation builds a computation graph and stores intermediate values so gradients can be computed during backpropagation. This is powerful, but adds memory overhead because each tensor that tracks gradients needs extra metadata and must keep its intermediate results. In small models, this cost may be minor, but in large networks or with high-resolution inputs, it can become significant and restrict batch size or even whether the model fits on your device. For this reason, controlling when gradients are tracked is important not only for correct training behavior, but also for efficient memory use and stable training and evaluation loops. Turning off gradient tracking reduces memory use by keeping certain operations out of the computation graph. When you disable gradients or detach a tensor, the framework treats the results as regular values and can free their memory once they are no longer needed. This is especially important during tasks like model evaluation or visualization, where you run the model many times without needing gradients for learning. As a result, you get lower memory overhead and smoother performance. Reducing how many tensors track gradients saves memory and speeds up both the forward and backward passes. By skipping unnecessary gradient bookkeeping, each iteration runs faster, and you can fit larger batches or more complex models on the same hardware. In production or large-scale inference, turning off gradient tracking makes the model behave like a fast, memory-efficient function. Even during training, disabling gradients for selected parts of the model can free resources and help experiments run without hitting hardware limits. Python code, memory, and speed. This lesson introduces how to control memory use in PyTorch's automatic differentiation system. It compares how tracking gradients affects both speed and memory. The focus is on two beginner-friendly tools, using the no gradient context to temporarily turn off gradient tracking, and using the detach operation to break tensors away from the computation graph. Together, these ideas help you manage resources more efficiently when training or evaluating models. The commented line is suggesting that you install PyTorch along with its related libraries, Torch Vision and Torch Audio. This setup step ensures that the environment has the tools needed for working with tensors and running deep learning tasks. These libraries provide the core features for tensor operations and automatic differentiation. They are essential for the script to run correctly and to demonstrate how PyTorch handles memory control and computational speed. We begin by importing the standard libraries for time, operating system access, and random number generation. These tools let the script work with timing functions, interact with the system environment, and create random values. Together, they support managing when code runs, performing system-level tasks, and controlling randomness so results can be reproduced. We begin by importing the PyTorch library so we can work with tensors and use its automatic differentiation features. These features, known as Autograd, allow us to compute gradients automatically, which is essential for training neural networks and many other machine learning models. Because PyTorch makes these operations flexible and efficient, it has become a popular tool for deep learning tasks. To make our script produce the same results every time it runs, we set deterministic random seeds. We first set the seed in Python's random library to 0 so that any built-in random behavior is controlled. We then set the PyTorch manual seed to 0 so that random operations inside PyTorch such as tensor initialization, are also repeatable. This reproducibility is especially important when debugging or comparing different runs of the code. This code chooses whether to run on a graphics processing unit or on the central processor, depending on what is available. It uses PyTorch to check if a CUDA-compatible graphics card is present. If such a card is found, the program runs on the graphics processor. If not, it runs on the regular processor. This setup helps the code use faster hardware when possible. We begin by printing the current PyTorch version and the device selected for computation. This step helps confirm that the environment is set up as expected, especially when switching between hardware like CPUs and GPUs. Knowing the exact PyTorch version also helps ensure that the code and any external libraries are compatible with the environment. Overall, this quick check reduces confusion and potential errors later in the workflow. We use a helper function to measure how long another function takes to run. It records the current time before the function starts, then runs the function and saves its result. After the function finishes, it records the time again and subtracts the start time from the end time to get the elapsed time in milliseconds. It then prints the given label and the elapsed time rounded to 3 decimal places, and finally returns the original function's result. We create an input tensor with 16,384 elements using PyTorch's random normal generator and place it on the available device, such as a GPU or CPU. We then enable gradient tracking for this tensor by setting its gradient requirement to true. This tells PyTorch's automatic differentiation system to record all operations involving the tensor so that gradients can be computed later during optimization. First, we check that the tensor has the correct shape and the expected number of elements for the model's input. We then confirm that it is configured to track gradients. This is necessary so that automatic differentiation works properly during training. With these checks in place, any later operations that rely on gradient computation will function as intended. This function computes a simple operation while tracking gradients for optimization. It first scales the input tensor by 2, then adds 1 to each element, and applies the ReLU activation so that any negative values become 0. It then takes the mean of the resulting values to produce a single loss value. Finally, it runs backpropagation on this loss to compute how the loss changes with respect to the original input, and returns the loss. This function runs a small computation in PyTorch without tracking gradients. It uses the no-gradient context so that gradient information is not stored. Inside this context, it scales the input tensor by 2, adds 1, applies the ReLU activation, and then takes the mean of the result as the loss value. The function finally returns this loss, making it suitable for inference or evaluation, where gradients are not needed, which saves memory and speeds up computation. We first run the function that does a forward and backward pass with gradient tracking turned on to warm up the device, so any initial setup or caching is completed before timing. Then we run the same computation again, this time without tracking gradients, to warm up that mode as well. This preparation ensures that when we later measure execution time, both the gradient and non-gradient runs are compared under similar, stable conditions. Before timing our computations in PyTorch, we need to clear any previously accumulated gradients. PyTorch adds new gradients to existing ones by default, which can interfere with accurate timing measurements. To avoid this, we check whether the tensor's gradient attribute exists, meaning it holds values from earlier operations. If it does, we reset these gradients to 0, so the computation starts from a clean state. We measure how long a computation takes when both the forward and backward passes run with gradient tracking turned on. A helper routine records the start time, performs the computation, then calculates the elapsed time. It prints this duration with a label indicating that it is the time for the forward and backward passes with gradients. This timing helps us understand the performance cost of enabling gradient tracking. To manage memory efficiently, we first check whether the tensor's gradient is present, meaning gradients have been computed and stored. If it exists, we call the method that sets this gradient to 0, clearing out the stored values. This prevents old gradients from accumulating across operations, which could produce incorrect results. By resetting the gradients, we also free memory and help maintain good performance for later computations. We measure the execution time of a computation while gradients are not being tracked by calling a forward pass function that runs without gradient calculations. This function is wrapped in a timing helper that records how long it takes to complete. By doing this, we can compare performance with and without gradient tracking. These measurements help us understand potential gains in speed and memory efficiency when gradients are not needed. We first check whether the loss computed with gradients still has gradient tracking enabled, which tells us if its computation graph is active. Next, we check the same property for the loss computed inside the no gradient context. Comparing these results confirms that the no gradient operation has successfully turned off gradient tracking, so this second loss no longer has an active computation graph. When we multiply a tensor by 3, the result still tracks gradients as long as the original tensor has gradient tracking enabled. If we then apply the detach operation to this intermediate result, we create a new tensor that shares the same underlying data, but no longer tracks gradients. This means any further computations using the detached tensor will not affect the gradient history of the original tensor. Detaching is useful when you want to break the gradient flow for certain parts of a computation, while keeping the data itself unchanged. We first check whether the intermediate tensor needs gradients by looking at its requires gradient attribute, which tells us if it is part of the automatic differentiation graph. Then we check the same attribute for the detached version of this tensor. Because we used the detach operation earlier, this new tensor should not require gradients and is no longer tracked in the computation graph. This allows us to perform further operations on it without recording gradient information, which saves both memory and computation time. We use a special context manager in PyTorch to turn off gradient tracking, so computations run faster and use less memory when gradients are not needed. Inside this block, we work with a detached tensor, meaning it is no longer connected to the computation graph. We take the absolute value of this tensor, then compute the mean of those absolute values. Finally, we convert this mean from a tensor to a regular Python floating point number using the item method, giving us an efficient result without the overhead of gradient tracking. At the end of the script, a summary value is printed that is computed from a detached tensor. This value is rounded to 4 decimal places to make it easier to read and interpret. The final printout serves both as a confirmation that the script ran successfully and as a concise summary of the computation performed on the detached tensor. This script illustrates how PyTorch's automatic differentiation affects memory use and execution speed. It runs the same computation on a large tensor twice, first with gradient tracking turned on and then with it turned off, and compares the timing. When gradients are tracked, PyTorch builds a computation graph, which makes the operation slower and more memory intensive. Without gradient tracking, the computation runs faster and uses less memory. The script also shows how to detach a tensor from its computation graph so gradients no longer flow through it, then confirms that this detached tensor does not require gradients and can be used to compute a summary value without tracking. Overall, it highlights the trade-off between speed, memory, and gradient tracking in PyTorch. In this lecture, you learn to describe how PyTorch builds dynamic computation graphs and uses them to compute gradients. Use requires grad, backward, and grad attributes to compute and inspect gradients for simple tensor operations. And control gradient tracking with torch.nograd and detach to optimize performance and avoid unintended graph creation. In the next lecture, Lecture B, we will go over modules and layers.
Thank you for your attention. See you all in the next lecture.